Okay, hi class. Hey, this is, as promised, a lesson on sections 10.2 and 10.3 from your textbook. And the basic topic here is the idea of bivariate data. I've got a couple of data sets here, and you can find these attached to the email that I sent. So I might suggest that you print these off, and then on the second page we're going to be doing some work with this, especially the height and weight data. And so you can kind of work along with me as we work through this. Also, make sure that you've got your calculator handy, because I'm going to show you some of the things that your calculator will do that I think you're going to find to be very, very beneficial, especially in working with bivariate data. Okay, so the three data sets that I have here is a sample of about 10 kids here. I'm going to say that these were taken from a roster from a high school football program. And it gives the height of a student, and it gives their weight in pounds. So height in inches and weight in pounds. And notice that we got some kids in here. This kid is about 6'4". We got another kid there that's about 5'10", and so on. And their weights are given over here. And then we got another data set over here that is the number of people that went out to dinner, number of people that were in the party, and then how much their total bill was. And down at the bottom we've got another data set that was taken from a group of students, and the question that was asked was, how many hours of sleep did you get the night before you took the ACT, and then what score did you get? And the very last one is some data that was taken from a mechanism that tosses a ball into the air, and this mechanism has the ability to measure the initial velocity measured in meters per second, and then how high the ball goes if the initial velocity is these numbers over here. Alright, so if you compare the type of data that we have here compared to what we've been talking about in class so far, there's more going on this data set than just talking about the center, talking about the spread, talking about any kind of outliers that might be in one of the data sets. But really what we're interested in addition to that, is a relationship between the two. Okay, for example, this guy is pretty tall, 6'4", and he weighs 200 pounds. If you compare him to this kid down here who is 65 inches tall, that's 5'5", he weighs 160 pounds. Alright, so it looks like this tall guy weighs more than the short guy weighs, which I think we'd expect. And so what we want to look at is, how are those data sets related to each other? How is the height related to the weight of a student? And I think that if you look through this data set, you can probably visualize a little bit that the taller kids tend to be the heavier kids. And so what we'd like to be able to do is talk about how we can display this as a graph. And then once we can display it as a graph, we want to be able to describe some of the major characteristics of that graph using some kind of a measure that is going to tell me some relationship between the two. Alright, so first of all, I'm going to show you some stuff that you can do on your calculator to make some graphical displays of this, which I think is a good place to start when we start talking about the idea of regression and correlation. Alright, so if you take out your calculator, we're going to put this data into the calculator. And so if you remember from the other day, the place where we spend a lot of time is under the Stat menu. Okay, we're going to go to Edit, and we are going to enter the data into some lists. Alright, so if your calculator is kind of like mine right now, you've got some numbers in the list 1 and list 2. That's where I want to put my data. So if you've got data in there, you can get rid of it by just putting the cursor up on the top of the list, and then hit the clear button, which is underneath the arrows. Right, and it appears that it didn't do anything, and it doesn't do anything until you hit enter. Right, and it'll wipe all the numbers out of that list. Right, then if you go over to list 2, hit the up arrow, and then hit clear, and then hit enter, and now we've got a clean slate to start entering numbers. Alright, so I'm just going to go down this list and enter 76, and then 70, and so on. Okay, and then I'm going to enter the weights. Just arrow over with the right arrow, and then enter the weights. Okay? Alright, if you're not caught up to me, you can always hit the pause button and pause this video until you get all the numbers in there. Okay, so what we'd like to be able to do is we'd like to be able to look at a relationship between these two sets of data. And I want to be able to see both sets at the same time. And so a kind of way that I'm going to look at this is like an algebraic ordered pair. Think about this as an x-coordinate and a y-coordinate. And then our graph is going to consist of just plotting a bunch of points in the plane. So for this first guy, I'm going to think about, here is my coordinate axes. This kid is 76 inches tall and he weighs 200 pounds. Right? And so we're going to end up with a point there for that particular kid. Then we got another kid that's 70 inches tall and he weighs 185. Alright, so we're going to end up with a point here for that kid. Alright, and we're going to do that for every single kid. Alright, now we could easily do this on paper, but I want to show you some things that you can do on the calculator that I think is going to save you quite a bit. Alright, so we've got the data entered. Now, what we did the other day to make a graphical display is we went to second, and then the button right above it says y equals, but above that it says stat plot. Alright, and this is the one that gives us the menu that we can choose the type of graph that we want. Alright, so choose that first graph. If it's not turned on, hit on, or just hit the enter button. And then the type of graph that we're going to be looking at is that first one. Okay, it looks like a bunch of points in a plane. Alright, so put the cursor on that and then you have to select it by hitting enter. And then it's going to ask us where is our x data and what's our y data. Okay, our x data is the numbers that we had in list 1. Okay, if it doesn't say list 1 there, you can just hit second 1 and it'll put that number in there. And then here, just second 2. Alright, and then the last line here is just what kind of a mark do we want. I'm going to choose the square just because it shows up best in this on the calculator. Alright, now the next thing we need to do is set the window so that we've got a decent window to see this data. Alright, and so if I go to Window, it's the second button underneath the screen, and I think about, we're going to have along the x-axis all these heights. Alright, my shortest kid looks like is about 65 inches, so I think I probably want to start this at about maybe 60. My tallest kid is 76 inches tall, so maybe I want to go up to about 80. The x scale doesn't make any difference in this picture. All it's going to do is put tick marks along the x-axis, so I can just leave that at 1. And then for my y min, my lightest kid here is 160 pounds. So I'm going to say let's start at 150 then. And my biggest kid is 215, so maybe go to 225. Right, and again, the y scale there doesn't make any difference what we put in there. It's just going to put marks along the vertical axis. Alright, then once I get all that set up, I can just hit the graph button. Okay, and I see this kind of a picture. Alright, now I want to show you one other thing that it may save you a little bit of work on this is if we go back to second y equals and we look at our setup here, actually once I get everything set up there, if I just hit second and then the quit button is right next to it, get back to my home screen, the calculator is smart enough that it could set that window for you. Okay, if you look at this button in the middle underneath the screen, it says zoom on it. And one of the features about this calculator that I kind of like is that there is a zoom, and if you arrow down to number 9, it says zoom stat. And what that will do is look at your numbers that you're trying to graph and it will just set the window for you. Alright, so if I go to zoom stat, it adjusts the window for me and so that I can see all the points in the plane. Okay, so if I were in front of you in class right now, I would say describe what you see. Right, and I think that a lot of people would say, well, I see 10 dots. Okay, I think that's obvious. We see 10 dots because we have 10 kids over here. All right, but what I really see is there's kind of a pattern here. And that pattern is that it looks like there's points that are down here in the bottom left and then there's points that are up here in the upper right, and it seems like the data kind of goes from bottom left to upper right. Right, and so one of the things that we're going to be talking about in terms of describing a relationship here between two bivariate data sets is that we want to talk about 3 things. Okay, one of those things is the direction. Okay, the direction of this one. All right, and I'm going to say that anything that goes from bottom left generally to upper right, we're going to say is a positive direction. Okay, in other words, small values of x are going to be associated with small values of y, and large values of x are going to be associated with large values of y. So small x's and small y's are going to be down here, large x's and large y's are going to be up here, and actually the medium-sized x's are going to be associated kind of with medium-sized y's as well. Okay, the second thing that we're going to be looking at is the strength. Okay, I'm going to look at this one and say, you know, these don't fall exactly along any kind of a straight line or a curve, but it looks like if I were to fit some kind of a function in here, it looks like it would, the points are going to be pretty close to some kind of a model. All right, they're going to be kind of clustered around some kind of a, some kind of a graph. All right, and so I'm going to say that this one, the strength of this relationship is relatively strong. Okay, in other words, if I know something about how tall somebody is, I probably have a pretty good idea about how much they weigh. Okay, and then the other thing that we're going to be looking at in terms of bivariate data is the shape. Okay. One of the shapes that we're going to be looking for is this idea of linear. All right, could you take a line and put it in here and those points are going to fall pretty close to a line, or a linear relationship is a pretty good description about how these things line up. Okay, if a distribution is not linear, another kind of a description would be maybe that it's curved. Okay, so maybe it's like an exponential function or some other kind of maybe a parabola or something along those lines. All right, so these are the three things we're mainly going to be concerned about. Now, what I want to look at is how do we describe these then mathematically? All right, and we're going to have a way to describe both the direction and the strength is going to be measured with something that's called the correlation. And actually we're going to end up coming up with a number that's called the correlation coefficient. And you're going to see that denoted by a lowercase r. All right, the correlation coefficient is going to be denoted by lowercase r. Okay, so what I'm thinking about is there's going to be a number that's going to describe if this thing has got a positive association or a negative association, and then in addition to that it's going to tell me how strong the relationship is. Alright, so what I want to look at is, suppose that we have some kind of a relationship that is, let's say, a positive association, very similar to what we have here. And let's say that that distribution maybe looks something like this. Right, now, there's a thing called a correlation coefficient, R, and that correlation coefficient is going to be determined by a formula. Alright, and the formula is got a lot of stuff going on in it. It's going to be take every x value and subtract the average x. Okay, so this looks a lot like what we did the other day in terms of finding standard deviations and finding z-scores. And in fact, this is going to be calculate a z-score for every x. Okay, and then we're also going to take the y values and we're going to calculate a z-score for every y value. Okay, so this just says take every value of y, subtract its average, and divide by the standard deviation of those numbers. Right, and then after we've calculated every one of those, this symbol just means we're going to add them all up. Alright, now if you think about what does this thing measure then? This is the correlation coefficient, and I want to know what is it going to measure. Alright, so if we think about x bar and y bar, this x is just the average of all the x coordinates of these points. So I would say that probably x bar is going to be a number right about here, somewhere in the middle of that set of data. And then the y bar is going to be just the average of all these y coordinates. So I'm going to say y bar is probably going to be somewhere about there. So then if we think about where that point is, x bar and y bar, right? And I'm going to think that this is a point just that's in the xy plane. And I'm going to use this point to separate the plane into a bunch of little pieces. Okay, actually into 4 pieces. We're going to separate the plane like this. Okay, And then what I want to know is something about the z-scores up here. All right, so if I take, let's say I take a point that's in this, I'm going to call it a quadrant. Okay, all these points that are in this quadrant, and I want to know something about their z-score. Right, so if you look at this point here, the x-coordinate of this point is bigger than the mean. So if I subtract these, I'm going to get a positive number. And then the standard deviation has to be positive. So up here I'm going to say z sub x. I'm going to say any z-score that's up here is going to be positive. All right, and I think that if you look at points that are down here, we can also say that that point, because it's to the right of the mean, is going to have a z-score that is positive. All right, if you look at points that are over here and points that are over here, these are going to have z-scores that are negative. All right, then if you look at the z-scores for y, if I calculate a z-score for this point, it's above the average y, so it's going to have a positive z-score. And the z-scores for y's over here are also going to be positive. This point's above the y bar. And then all these points that are down below that horizontal line are going to have z-scores for y that are negative. Okay, so really this thing right here is calculate a z-score for x. This thing is calculate a z-score for y. The symbol in between these is multiply them together. All right, so if you think about, here's two positive numbers. I'm going to multiply them together. Every one of the points that is in this upper right-hand quadrant is going to give me a positive number times a positive number is going to give me a positive result. Anytime I've got a point over here in the second quadrant, we'll call it, we're going to end up with a positive y but a negative x. And it's going to give me a negative product. The ones that are down here are going to give me a negative times a negative is positive. And the ones in this, I'll call it the fourth quadrant, are going to give me a negative. All right, and then this says we're just going to add up all those products. All right, so if you look at this particular distribution has a lot of points that are in this quadrant and a lot of points that are in this quadrant, and all of those are going to give me positive contributions to this this correlation coefficient. And then we've got a point here and a point here that are going to contribute a negative. All right, so we're generally going to end up with positive numbers here. So if my data kind of goes from bottom left to upper right, it looks like the positive numbers are going to outweigh the negative numbers. All right, and then you can look at this formula and say, this is a mess to try to calculate. Okay, but I'm going to show you how to use the calculator to do quite a bit of this work. All right, so if you flip over to the next page, this describes that idea again about the correlation coefficient. I forgot one thing here. On my formula, I also have to take this thing and I'm going to multiply it by 1 over n minus 1. All right, so it's kind of an average of all those products. So we're just going to divide this by 1 less than the number of points that I have. Okay? All right, so I want to take a look at that first data set. And here are all the numbers again. And what I want to do is calculate a z-score for every one of the x's, calculate a z-score for every one of the y's, multiply them together, and then I'm going to add them all up and divide by the number of contributions. All right, so in order for me to do this, I'm going to need to know what x bar is. All right, we saw that on Tuesday night. To find the average of all these x's, okay, remember, here's where my numbers are. Right, and I think that these are all the same numbers that I have in this list. Yeah, it looks like it. All right, so I want to find the average of all the x's and the standard deviation of the x's. And if you recall from Tuesday night, it's under Stat, Calc, one variable stats. Then I have to tell it on list 1, which is just second 1. And it tells me that the average height is 69.6. And the standard deviation of all these I'm going to write as 3.44. Okay? Then the next thing I want to do is look at what's the average y and what's the standard deviation of the y's. So if I go to Stat, Calc, one variable stats, but now do it on list 2, the average weight of these kids is 184.5. And the standard deviation is about 19.5. Okay, so if I look at this first kid, I want to calculate his z-score. All right, so by the formula, it says take 69.6, take his height, 76, subtract 69.6. All right, then I'm going to hit enter. And so this kid is 6.4. That's going to tell me that he's 6.4 inches above the average. And then we're going to divide that by the standard deviation, which was 3.44. Okay, so he's going to have a z-score for his height that is 1.86. All right, so I'm going to put that number right here. 1.86. Okay, then I'm going to go to the next kid, and I'm going to say take 70 minus 69.6. Okay, he's 0.4 inches above the mean, and then we're going to divide him by a standard deviation, 3.44, and we get a contribution here of 0.116. I'm going to just call that 0.12. Okay. All right, so if you look at what these numbers represent, these are z-scores. This first kid is almost 2 standard deviations above the mean, and this kid is just barely above, 12 100ths of a standard deviation above the mean. Okay, I've got 18 more of these to fill in, and I could do each one of those individually, but I think what I want to do is have my calculator do some of this work for me. All right, so I'm going to go back to Stat Edit, and I'm going to use my calculator almost like I'm using it as a spreadsheet. All right, so I'm going to go over here to List 3 and get rid of the stuff in List 3, and I'm going to use List 3 to do these calculations. All right, this is kind of nice. If I go arrow up to the top of List 3 and hit Enter, and I want to put this formula into the calculator. All right, so I got to start with a left parenthesis. The left parenthesis is the value of x. So to get this 1.86, I took 76, okay, and then I subtracted the mean and divided by the standard deviation. We're going to do that same thing to every one of these points. So I'm just going to tell the calculator, look in list 1, so second one, minus the mean is always going to be 69.6 for this data set. Close that, and then divide by 3.44. All right, and I get all those z-scores all in one shot. Okay, that's pretty nice. Okay, so I'm going to just write all those down. So this next kid is a negative 0.465. I'm going to write him as just negative I'm going to write him as 47. And then the next one is negative 0.17. The next one is a positive I'm going to call it 12. The next one is a negative 1.34. And then a negative 1.05, and negative 0.76, and the next one, positive 0.41, and the last one is 1.28. Okay, one thing that you should notice is that if I were to add all these numbers together, I'm going to get exactly 0. Okay, well, I shouldn't say that. I should get 0, possibly not with a little bit of rounding. Okay, so now I want to do the same thing in this other list. Right? I want to calculate the z-scores for their weights. Right, so let's go over to list 4, put the cursor up on the top of the list, hit clear, and then I can start typing in this formula. So this formula is going to be left parenthesis. We're going to take their weights, which are all in list 2. We're going to subtract their mean, 184.5. Close that parenthesis, and then we're going to divide by the standard deviation, 19.5. Right, and then hit enter. Alright, so my first guy, he's got a z-score of 0.79. The next one is a 0.03. The next one is negative 0.74, and then a negative 0.49, and a positive. Let's see. Next one is 0.79, The next one is negative 1.26. And the next one is the same thing. And then negative 0.49 and 1.05 and 1.56. Okay, so those are the z-scores for their weights. So this guy here, he's 0.79 standard deviations above the mean for his weight. So he weighed 200 pounds. Okay, he is, what, about 15 pounds above average, but a standard deviation is 19, so we take about 15 divided by 19 is going to give me how many standard deviations above the mean he is. Alright, now what we're going to do next is multiply all these together. Right, and so we can do that on the calculator as well. And we're just going to go over to list 5. And in list 5, I'm just going to put in a formula. And that formula is take the numbers in list 3 and multiply by the numbers in list 4. So list 3 times list 4. And I get a bunch of numbers here. 1.48 and 0.003. and 0.346. And maybe I should take these out to a few decimal places every time. And then the next one is 0.085, and then 1.68, and 1.315, and 0.368, and 0.428 and 2.000, and it looks like I'm off one. Dang it. Okay, let's see, where did I get off? Oh, I missed one in here. Okay, there should be a 0.092 in here. All right, and then the rest of these should all be slid down one. Alright, so what you should notice then is that all these numbers end up being positive. Right? And they end up being positive because these two are positive, these two are positive, these two are negative. We're multiplying those together and we get a positive result. And I think every combination in here gave us a positive product. Right? Which means that we're going to end up adding up a bunch of positive numbers. Alright, now the next thing I want to do is find out what's the total here, and then we're going to divide that by, there was 10 kids here, so we're going to divide by 9. Alright, so to find the sum of this list, I can get out of here. Just hit second quit, and then hit second stat math, and there's a sum command here, and I want to find the sum, and all those numbers were in list 5. Okay, so we get 7.796. And then I'm going to divide that by, or multiply by 1 over, this number is going to be 9. So we're going to divide that by 9, and I get 0.866. Okay? Alright, so now that's a number that describes something. Alright, we said it's going to describe the direction, and it's going to describe the strength. Alright, so if we think about the direction, this picture that I gave you here shows a direction that it looks to be positive. Alright, and because that correlation coefficient is positive, we're going to have a positive association here. Okay, so a positive association is going to look like this. A negative correlation is going to look, more or less like this. Okay, in our case, we got a positive number. Alright, then we're also looking at the strength. Right, and I'm going to tell you that the correlation coefficient has to always be a number that is on the scale from -1 to +1. Right, and in order for us to determine the strength here, we're going to have to think about, well, this is one of those things where we're just going to have to visualize and say, this is where I'm going to cut off and say this is a strong correlation and this is a weak correlation, and so on. All right, and I have a way of doing that. If again, if I was up in front of you in class, I've got this software package that really does a nice job of showing some things. Right, and what I want to look at is a different data set. Let's see, where is it? File, let's do open, and what was it? It's this one, seeing R. Yeah, this is it. Okay, so here's a scatter plot, just kind of a generic set of data. I think this was how students scored on a test 1 and how they scored on test 2. And if you look at this picture, I think most people would say, I don't see much of a correlation here at all. It's just a kind of a scattering of points, okay, just a cloud of points. And the way that this is set up is this is on a slider. And what I've done is I've set the correlation coefficient over here to be 0.003. So this correlation in this picture is almost 0. And if you end up with this correlation coefficient that's almost 0, this is what you're going to see, is just a cloud of data. Right now, this software has the ability to take that correlation coefficient and change it. And you can see that as I change the correlation coefficient, we're going to, those points in the picture move, right, which is a little bit deceiving because the correlation coefficient doesn't drive the location of these points. It's actually where these points are determines the correlation coefficient. But what I want to do is, and if I had this in front of you in class, what I would say is we're going to be looking for a couple of different gradients here. I'm going to say, tell me by raising your hand when you look at this distribution and you say, I see a positive association there. Okay, when you start to see something that looks like there's a relationship that's positive. All right, I'm going to take this thing and slide it over here to the right. You're going to tell me when would you say that that is just positive. Okay, and then after I do that, then I'm going to say, when would you say that that relationship is strong? Okay, and I would just have you guys all raise your hands. Okay, so we're looking at where do you just see a moderately strong, and then where do you see something that you would call strong. All right, if I slide this across, what I've found in the past is generally when I get to about around 0.6 or so, people start to see that there is a positive association here between these two sets of data. All right, and then what I would have you do is by a show of hands, tell me when would you say that that correlation is strong. And generally it's been my experience that when we get up to about 0.9 or higher, that's when people start saying, this looks like a really strong positive association. There's a strong relationship between these two sets of data. Right? And then I told you that we can't get any bigger than 1. And what happens when we get to the correlation coefficient is equal to 1, right? The software is a little bit quirky that it lets me go past 1. But if the correlation coefficient is exactly 1, we're going to end up with an exact linear relationship. Okay? So a relationship of about 0.9 is pretty strong. Anything from 0.9 to 100% is going to be pretty strong. Anything that is less than that, you know, like around 0.6 to 0.7, we're going to say is a weak positive. Anything that's between like negative 0.5 and positive 0.5, I'm going to say is going to be just a weak relationship. All right, and then the same thing happens over here. When we get over here to negative 0.9, the relationship here is strong, but it's negative. And then if I get over here to negative 1, okay, we're going to find that those points are going to line up exactly. Right? They disappear when you go past negative 1, but if I set this equal to negative 1, they line up perfectly on a straight line. Okay, so correlation coefficient is going to tell me the direction. Correlation coefficient tells me about the direction. If the correlation coefficient is positive, it has a positive relationship. If that correlation coefficient is between about negative 0.5 and 0.5, we're going to say it's weak. If it's between 0.5 and about 0.9 or so, we're going to say it's moderately strong. And then anything above about a 0.9 is going to be a very strong relationship. And then same thing on the other end. If we get a number that's between like negative 1 and negative 0.9, that's going to be a strong but negative relationship. Okay, so correlation coefficient measures those two things. Now the shape is something that we're just going to have to visualize. All right, if I go back to my graph again, what was it? Go back to, not this graph, the other one. Height and weight data. All right, I'm going to look at this and say, you know what, if I could fit a line in here, I think a linear function is probably going to work just as well as anything else. Okay? Right, and so that's what we're going to end up doing, is trying to fit a line to this data. All right, now I want to, if I were doing this with you in class, I would take each one of these data sets, and I think I would have you just make a guess on what you think the correlation coefficient is. All right, this correlation coefficient was 0.866. Okay, and 0.866 is about 0.9. This is a pretty strong positive association. And I'm going to tell you also that the correlation coefficient here is about 0.868. Okay, it's kind of just by coincidence that those two things are almost the same thing. But if you think about how much a bill is going to be for your dinner, it is closely related to how many people were eating there. Right? So 10 people, the bill is going to be fairly high. 1 person, the bill is going to be fairly low. So it makes sense that the correlation coefficient would be relatively high here. Right, down here, we've got number of hours of sleep a student got before they took the ACT and the score that they earned on the exam. Right? I would say that probably knowing how many hours of sleep a person got the night before their test is not going to be very closely related to the score they actually got. All right, I think that probably a better variable here might be what is their high school GPA, or how many hours did you prepare for this exam. Right? And I don't think that we'd be too surprised to see that the correlation coefficient down here is fairly low. Right? And it is. It's about 0.17. Okay, pretty low. I'm sorry, was that 1.17? Hang on, let me double check that one. Yeah, I think that one was about 0.17. Now that I'm thinking about that, I think that I got these switched around. This one I think actually was, the correlation was 0.02. Right? Either way, those are very, very small. All right, and then this one is, we've got this catapult that's going to throw a ball up into the air, and I can control the initial velocity, how fast it comes off the catapult, and then how high does it go before it starts to come back down. I think that this correlation coefficient was 0.17. Okay? All right, positive, but not very strong. Okay, so that takes care of the idea of correlation. Now, the other thing I want to look at is this data is fairly linear. Okay, this number of people in the party and how much the bill was. This, I think you could probably say the correlation coefficient is 0.02 is probably just going to be a scatter of points. And then this one, it looks like the faster it comes off the catapult, the higher it goes. So I do want to take a look at this distribution and talk about it, because this one is a little bit different than the other ones. All right, so again, let's go back to our calculator and let's put in, so go to Stat Edit. We're done with the data that's in here, so let's go over to List 1 and let's clear out List 1, and let's clear out List 2, and let's put this data in. So 2 and 5, 6, 9, 10, 11, 12, 16, 20, 25. And then over here, we got 3.9, 8.7, 11.2, and so on. Okay, now if I go to second y equals, all right, this should already be turned on and everything should be set, because all I did is I changed the numbers that were in those lists, but we're still going to graph those two lists. So I get this all set up, and then I can just hit zoom and then go down to number 9 is zoom stat. All right, so if you look at this data set, I would say that people would look at this and say correlation coefficient is fairly high. Right? I'm going to go back and recalculate this one because I don't think it's 0.17. I think it's higher than that. All right, it's definitely positive. It goes from bottom left to upper right. All right, but if you look at this closely, it looks like there's not a straight line here. It looks to me like this line kind of bends a little bit, that there's some curvature to it. And so the shape of this one, I would say, is there is a relationship here that is pretty strong, but I would say it's not necessarily linear. Okay, it looks to me like this is going to be some kind of a parabola or some kind of an exponential function. All right, so for this one, even though it is a strong positive association, it doesn't look like it's linear. Okay? All right, so that should take care of a lot of the stuff that we want to talk about in terms of correlation. The other part of this is something that's called regression. All right, and the regression has to do with finding the equation of a line that fits the data pretty well. All right, now I'm going to show you just kind of generically what I mean by a line of best fit, and I'm going to talk to you generically about what it means to be a line of best fit, and then we're going to look at a couple of different situations where we're going to use that. All right, and I think the best way to demonstrate that is to go back to my software here, and we're going to fit a line to this data. All right, and if I click on the graph, I can say, give me a movable line. Okay, so what I want to do is take this line and say, this is basically the trend of the data. I'm just going to take this line and I can move it around a little bit, and I can fit it in here in such a way that I think I could probably convince most of you that that looks like a pretty good fit. Right? And one of the things that I would ask in front of the class is, what makes that a line of good fit? And I would bet that somebody would tell me, well, there's about the same number of points above the line as there is below the line. Okay? And I would hope that somebody would say that so that I could tell you that that's not really the criteria, because there are, well, there's 4 points above and there's 6 points below, but I think I could probably take this line and do something like this, and you would still say that this is a pretty good fit. Okay? 5 above and 5 below. Right? But I could take this line also and say, let's put it like this and like this, and say, you know what, there's 5 points above and there's 5 points below, but I think everybody would say that's not a very good fit. All right, so it's not that the fact that there's 5 above and 5 below, which generally that is going to be true, that there is going to be half above and half below, but really what we're looking at is we want to find that we're going to minimize the distance that these points are away from the line. All right, and those distances we're going to refer to as residuals. Okay, a residual for this kid up here is how far is he above the line. And when I say above the line, I'm talking about a vertical distance between him and the line. All right, and then what I want to do is move the line around in such a way that I minimize the sum of all those residuals. Right, and then this software is really nice because I can say, show me these squares. Right, so if you think about this kid here, the distance from that point to this point is the residual. And then what we're going to do is square that, okay, because this guy's going to have a positive residual, this guy's going to have a negative residual. This guy's positive, this guy's positive, this guy's a negative, this guy's a negative, and so on. And what would happen is, if we ended up with about half the points above and below, those residuals are always going to just add up to 0. What we really want to do is square all those residuals. So visually, if I take this residual, this distance, and square it, I'm going to get the area of this square. If I take his residual and square it, I'm going to get the area of this square. So the idea is we want to find the line that is going to minimize the sum of the squares of the residuals. Basically the sum of the areas of those squares. All right, and the name of the line is actually called the least squares regression line, and that's why it's called that. All right, so I'm going to take this line and move it, and if you notice down here at the bottom of the screen, it tells me what the sum of the areas are. All right, so as I move that, you'll see that number change. All right, and then the idea is that there's going to be some point in here where I can find the very smallest value that that's ever going to take on. All right, and I'm going to just mess around with this a little bit until I can get something that I think looks close. And I would say that somewhere around 850 or so looks like it's going to be the smallest number that I can get. Okay? Now, there is a lot of mathematics and calculus involved in finding the one line that does fit the best, but I would tell you also that visually, I think we can come pretty close to finding that line. I'm going to say that this is a pretty good fit. Okay, this software will allow me to do something that's called show me the least squares regression line. Okay, and you can't hardly see it because they're almost exactly the same. If I move that brown line around again, okay, the other line you see there is the actual least squares regression line. We're almost right on top of it. Okay, so let me clean this up a little bit. I'm going to get rid of the squares and I'm going to get rid of the movable line. This is the least squares regression line. Okay, coming up with that equation is not something that I'm going to expect that you are ever going to do by hand. Okay, but the equation, if you look at it down there at the bottom of the screen, is negative 157.6 plus 4.915, I'm going to say 92 times x. All right, and what I'm going to expect that you guys do is instead of just putting y's and x's in there, I want to put in, let's see, let me get back to my camera. All right, we're going to put in the equation of the line here, and the y values go on this side of the equation, the x is going to go here, but the y values are weight. All right, I'm going to say, we're just going to put the word weight in there. And then I'm going to put a hat on top of it because that hat indicates that that is an approximate weight. And then the x value is their height. Okay, so this formula says that if I want to predict how much somebody weighs, all I have to do is plug their height into this equation and then approximate their weight. Okay, so an example of this. Suppose that this is a football roster and I'm the coach. And I have one kid that forgot to tell me what his weight is. Okay, but I do know that his height is 72 inches. I know he's 6 feet tall. So if I want to know what his weight is, all I have to do is take this equation, negative 157.6 plus 4.92, and plug his height into this equation, and that's going to give me an approximation for his weight. All right, so negative 157.6 plus 4.92 times 72. Okay, this model predicts that this kid is going to be 196.6 pounds. All right, so if I wanted to guess, a number to put in the roster for him, I'm going to say I'm going to put 196 pounds or 197 pounds in the roster for him. Okay? All right, so that's how you can use that least squares regression line. All right, now, to come up with that equation, okay, you might be looking at this and saying, well, I don't have that software on my computer, but you do have that software on your calculator. All right, so this is a nice built-in feature on the calculator as well. To find the equation of the least squares regression line, it is under Stat, under Calc. Okay, this is the same place where we find the one variable stats. And if you go down, there's a linear regression, number 4, and there's also another linear regression, number 8. These two functions are going to do exactly the same thing. The only difference is, in this equation, A is the coefficient of x, namely the slope, B is the y-intercept, and then their roles change down here. Okay, I'm going to say that in statistics, we're almost always going to call the slope B. And I don't know why they decided to do that, because probably your algebra books call the y-intercept B and the slope M. All right, but we're going to use this equation. All right, so select it, and then it's going to expect that I'm putting something in here. And I want to find the least squares regression line for the data that I have here. All right, now actually, the data that I had there I wiped out, unfortunately. So let's see. I know what I can do. All right, instead of finding the least squares regression line there, I have this data in my calculator now because that's what I put in. Let's see if I have that data somewhere else. You know what, just to show you that I'm going to get the same equation, I'm going to enter that data again in my calculator. So, all right, the problem is that this data I changed. I think, let's see if I have this. I might be lucky enough that I saved this at one time. Height. Okay, those look like they're in sorted order though. And I think those are the heights of students for our class. All right, I'm going to have to redo this. So 76. Okay, if you want to fast forward the video, this would be a good place to do it. And then 70, and then 68, 69, 70, 65, 66, 67, 71, 74. And then my other list, 200, 185, 170, okay, then we're set to go. All right, so now that again was stat, calc, arrow down to number 8, or you can just type in 8. All right, and then I want list 1, and then I got to separate this with the comma. The comma is right above the 7 on the keypad. So list 1 and then list 2. All it is where my x's are and where my y's are. Okay, and then when I hit enter, all right, I see the equation says y equals a plus bx, and then down below it tells me what a is. Okay, a is 157.6. That's the same number that we got off the computer, and 4.92. All right, then notice also it gives me the r and the r squared. And you may be looking at your calculator and saying, my calculator doesn't give me that number. All right, so you got to tell the calculator that you want to see that number. There are a couple ways to do that. One way that will work for all of your calculators is to go to second and then hit the button that corresponds to 0. Okay, and this is going to give me the catalog. This gives me everything that's built into the computer or into the calculator. All right, and what I'm looking for is a command that's called diagnostic on, and I could just scroll through all these, but there are a lot of commands in here. All right, if I want to get to where it says diagnostic on, I want to jump to the ones that start with the letter D. And if you notice above the this x to the -1 power button, there is a green D on my calculator, right? Or it might be in yellow on yours. Okay, and I'm just going to hit the alpha key and then hit that x to the -1. Okay, and what should happen is it should jump to the ones that start with D, and then I'm going to go down to where it says diagnostic on, and then just hit enter. All right, then if you run that same command again, the linear regression, okay, then you should see the r and the r squared. Okay, the r was 0.866. Okay, so that's a nice way to do this. And then the other thing that I want to do is take a look at how this line, how it looks compared to the data. All right, so if I go to y equals, I can type in -157.6 plus 4.92 times x, and then graph it. Or actually I need to do a zoom 9. Zoom 9. Alright, so there's my line of best fit. Okay, and that's exactly the same line the computer gave me. Alright, so a couple things that we're going to be doing here is you should notice that when you do linear regression, you can get this correlation coefficient. That's the way I'm going to expect that you're getting the correlation coefficient, is just running a regression and then looking at what the R says there. You also get the equation of the line. Okay, now in addition to the stuff that we just did, I want to look at what these numbers tell me. Alright, so in the context of this problem, this 4.92 has some meaning. And I'm going to expect that you can pick out what the meaning is. And if you remember from algebra, the slope of a line just tells you the change in y divided by the change in x. Right? And I think if we can look at the units on that, that should kind of give us an idea what it measures. So the slope of this line was 4.92. And slope is change in y divided by change in x. Okay, the change in y here is measured in pounds. Okay, y was in pounds and x was in inches. Okay, so if you think about what this measures, it's pounds per inch. Okay, so what this model predicts is that on average, when somebody gains 1 inch in height, they're going to gain about 4.92 pounds. Right? And again, that's on average. That's what the model predicts, which kind of makes sense. The taller you are, the more you're going to weigh. Okay? Now, the other thing is the y-intercept. The y-intercept in this case is negative 157.6. And I'm going to say that this one doesn't make a whole lot of sense, because what the y-intercept is equal to the y value when x is 0. Alright, so when x is equal to 0, what we're saying is if you put 0 in here for height and then calculate what the weight is, you're going to get negative 157.6. Well, there's two things wrong with that. First of all, we're probably not going to use this model to predict somebody who is 0 inches tall. And secondly, nobody weighs negative pounds. Alright, so for this one, this y-intercept really does not make a lot of physical sense, but it would mean how much somebody would weigh if they were 0 inches tall. Alright, I want to give you the equations of the other lines and then see if we can interpret what they represent. So for this one, if you go through and you calculate the bill or the model for this, you're going to get that the bill is approximately 16.50 plus about 8.50 times x, which is people. Alright, so if we interpret what this 850 represents, okay, again, the units are going to be change in y, that's money or dollars, per person. Alright, so what we're saying then is that on average, the bill is going to increase by about $8.50 for each additional person that joins the party. Okay? The 1650 represents how much the bill would be on average if nobody showed up to eat. Okay, so if you think about this, might be like you got to pay some kind of a fee to make a reservation and then you cancel. Nobody comes to eat. They still charge you $16.50. All right, that might be an interpretation of that one. Okay, the next one, the number of hours of sleep and the score on the ACT. All right, I'm going to tell you that the model for this one is, when I put this in the calculator, was ACT was about 19.5 plus 0.46, and then this was hours. Alright, so this 0.46, that represents, again, change in y. Okay, the change in y is, again, just points. And then this is number of hours of sleep. So if you take points over hours of sleep, this is points per hour of sleep. So on average, we're going to say a student is going to gain about a half a point for each additional hour of sleep. Okay? All right, that's what the model says. Then this one really does have some physical meaning. Right? And what it means is what a person could expect to get if they got 0 hours of sleep. Right? So the model predicts that if you pull an all-nighter, you're going to get 19.5 approximately. Okay? Then this last one, you're going to end up with the height is equal to negative 27.66 and then plus 6.16 times whatever the initial velocity is. Okay, so this thing would be how much the height, the maximum height, is going to increase by increasing the velocity by 1 meter per second. Okay, so it's the additional height that you gain by firing it at a higher initial velocity. And then this one again doesn't make a lot of sense. This one says that if you have an initial velocity of 0, the height is going to be negative. Right, well, actually, the model should predict that if you have a 0 initial velocity, it's not going to go anywhere. All right, so this negative 27.66 is kind of like the negative 157.6 up here. Okay, doesn't make a lot of sense. Okay, So I did all these calculations actually on the calculator, and it might be good for you to practice that on the homework. You've got several problems where they ask you to find the equation of the least squares regression line, find the correlation coefficient, and doing that on the calculator is the way that I'm going to expect that you do that. So you should be able to get through the homework from 10.2 and 10.3. The idea of linear regression and correlation is a fairly big topic in statistics. In this particular course, we're going to only talk about it, you talk about 2 sections in chapter 10, right? But those are pretty important sections. There's a lot of stuff that we do with statistics that are correlation. Right now, the other thing about correlation is that people abuse it quite a bit. And what I mean by that is they make a statement about if there's a high correlation, that means that there is a cause and effect relationship. Okay, there's a fairly high correlation here. 0.866 is a strong correlation coefficient. All right, but your height doesn't really cause your weight. Okay, the number of people in the party doesn't really cause what the bill is. Okay, there's other things involved. Okay, for example, this one, the amount of money that a bill is going to be dependent upon how many people are there, yes. But it's also going to depend upon some other things like what did they eat? Did they have a salad? Did they order cocktails? Did they, things like that are also going to contribute to this bill that is different than just the number of people in the party, right? But this correlation coefficient is pretty high. That tells me that the number of people in the party is probably the one variable that explains the most. Okay, same thing here. Knowing how tall somebody is does a pretty good job of explaining how much they weigh. Other things that would contribute to a person's weight would be, of course, body mass index, maybe their waistline, different things like that are also going to contribute to how much a person weighs. Down here, very little of this correlation is going to be dependent upon, or ACT score is going to be very loosely related to how many hours of sleep the student got the night before. Okay, and we see that here. This is a very weak correlation, right? So it wouldn't make any sense for me to even, conjecture that hours of sleep the night before the test is going to cause your grade to go up. Okay. Another thing that I always talk about at this point is that there was an honest-to-God study that went on, and it was a study that gave a relationship between shoe size and reading ability. Right? And they took all these kids at this elementary school and they measured their shoe size, and then they also gave them a reading test. And they found that there was a really, really high correlation between shoe size and reading ability. Right? And they published that shoe size causes high test scores. Right? Which I think you should probably think about that probably is not necessarily the case, that it's going to cause high scores. Right. Then, if you read further into the study, you also found out that the study was done with kids that were from kindergarten to 5th grade. Right. And then I think with that idea, then that probably casts some light on what's really happening. Okay, if you gave a reading ability test to kids that were from kindergarten to 5th grade, those 5th graders are definitely going to outperform the kindergartners in reading. Right. And if you think about their shoe size, those kids that are in 5th grade are going to have bigger feet as well. Right, so there is a high correlation between reading ability and shoe size, but the shoe size certainly does not cause the high scores in the reading ability. Okay, now there's actually something in there that's called a confounding variable, and that confounding variable is obviously the age of the kids. The older kids have higher reading scores, but they also have higher shoe sizes, bigger feet. Okay. Another study that I've seen is that they did a study on some of the beaches in Florida, and they said, that they did a relationship between how much ice cream was sold on the beach and how many drownings there were. And they found out that there was a really, really high correlation between how much ice cream was sold and how many drownings there were. And I think that the wrong conclusion there is that these people ate ice cream and then they went out and swam, and then the ice cream eating caused them to drown, which is probably not the case. Right? And I think if you think about what a confounding variable might be in that case, I think you could look at when do they sell more ice cream? And more ice cream is going to be sold on days that are really, really hot. Okay, and if you think about when are there going to be more drownings, there are probably going to be more drownings when there are more people on the beach. And if you think about the temperature is going to affect both of those things. When it's warmer, there's going to be more ice cream sold. And when it's warmer, there's going to be more people on the beach. If there's more people on the beach, there's naturally going to be more drownings. All right, so it's not that the ice cream is causing the drownings, even though there is a high correlation between the two. The confounding variable there happens to be the temperature. Okay, so be careful reading into that a high correlation certainly does not imply a causation. Okay, that's one of the things I really want you to get out of this, is that high correlation does not cause, or high correlation does not mean that there's a cause and effect relationship between the two variables. Okay, the score is related to sleep loosely, but the number of hours of sleep does certainly not cause the score. Okay, same thing over here. The number of people in the party does not cause the bill. It contributes to the bill, but it's not necessarily a cause and effect relationship. Your height does not cause your weight. Okay, those are things that a lot of people read into studies, and it's an improper way to do it. Okay, I've talked long enough. I think that you should be able to get through all the stuff in 10.2 and 10.3. Make sure that if you're not sure about how to use your calculator, go back through this video. And then one of the nice things about having a video is you can stop it, rewind it, play it again, and see how to enter the data in the calculator, how to come up with the least squares regression line, and all that stuff that I did. One thing you are not going to be required to be able to do is, I don't expect that you're going to find the correlation coefficient for some data by going back and doing what I did in that table, right, this table. Okay, the stuff I did here, you're not going to be expected to do that on a test or a quiz. If I asked you to find the correlation coefficient of this data over here, what I'd expect you to do is just put those in the calculator, run a least squares regression, and when you do that, you're going to get the correlation coefficient right from here. Okay, you don't have to do all this. All right, one very last thing I want to look at is there is something that's called influential points, and this program does a nice job of talking about that. All right, so if I talk about this kid right here, this kid is a relatively tall kid, but he's also kind of skinny. Right? He's below average, or below where he ought to be for his weight. So suppose that the coach told this kid during the summer, I want you to gain some weight. So this kid is going to move in this least square, or in this picture, he's going to move up this way. And what I want to know is, there are going to be some changes that happen to this equation, the least squares regression line, and also some changes in the correlation coefficient. So if I take this kid and move him up, okay, and I wish I could do this in front of you in class, I would ask people to tell me, what do you think is going to happen to the slope of this line? Is it going to get steeper or less steep? And then the other question that I'm interested in is this correlation going to increase or decrease? All right, and I think, if you think about both of those, I think that they're both going to increase. Okay, the slope of the line is going to go up. Okay, I see that happening. And then also, if you look at what happens down here, this is r squared, but not r. But r squared is getting bigger if I do that. Okay, so this guy out here, he's an influential point. Moving him around changes a lot of stuff in this equation. Now, if I did the same thing with this guy and moved him up, the line is going to get less steep actually, and the correlation coefficient changes a little bit, but not quite as much. Okay. And if I take this kid who's in the middle and do the same thing with him, okay, move him up, right? He doesn't have much effect on that line at all, and he also doesn't have much effect on the correlation coefficient. Right? So influential points are going to be points that are on the extremes, generally speaking. They have large x values or very small x values, are typically going to be referred to as influential points. right? And the book talks about those a little bit, which ones influence the points quite a bit. And then there's some other graphs that I think you should kind of get an intuitive idea about what's going on. And those are addressing some of the homework problems. Okay, so again, I have talked more than I should have here, but I wanted to make sure that you got everything from 10.2 and 10.3 that you needed. You should be working through the problems on the syllabus from 10.2 and 10.3, and I will be back on Tuesday of next week, and we won't have a quiz on Tuesday night, but there will be a quiz on Thursday night that will include some of the stuff from correlation and regression. So come with your questions on Tuesday, and then on Tuesday we're going to move on in the syllabus. Okay, have a good weekend, and I'll see you on Tuesday. Bye.